Okay, perfect. Okay, welcome everybody to another MCRN Colloquium. Today we're very lucky to have Dr. Deborah Sulsky, Professor Emeritus at the University of New Mexico. I'm really excited. I met Deborah for the first time, I think, in 2017 when I was a postdoc at SAMC. I got to work with her on a couple of things for a few years, and certainly she maintains one of my favorite rheologies for Seaice. So it's always nice to get to hear from her and interact from her, and I hope you'll enjoy too. So with that, today Deborah will be talking to us about Seaice mechanics on the surface of a sphere using the material point method. And please, with that, take it away.
Well, thank you, Christian. It's great to see you again, and boy, it makes me feel old thinking how long ago that was when we first met. The work that I'm going to talk to you about is part of a SIDAC project, a DOE-funded project. And before I get into details, I want to make sure to acknowledge all of my collaborators. And so there's University of New Mexico people, and Colorado State, and RPI, Los Alamos, and Sandia collaborators. And they've all taken part in this and helped with it. So I just want to make sure that we get them in here. So what I'm going to talk about, a little bit of background about the DOE Earth System modeling, a little bit of background about Seaice modeling, and a little bit of background about the material point method. I'm hearing an echo. I hope other people aren't hearing that. Let me know if the audio is not good. And so after the MPM, I'll concentrate on what we had to do to get MPM working on a sphere. So material point method is sort of a general method for solving continuum mechanics problems. But as far as I know, it's not been implemented on the sphere before. And then I'll talk about our code verification, and I'll show you a simulation of Arctic sea ice. I had in here some other aspects of the project. It's more than just this development of MPM, but I think I put time permitting, but I think time is not going to be permitting, so I've kind of crossed that out. I may mention some things at the end just to give you a feeling of other things we're doing, and then conclusions. Excuse me. Okay, so the DOE model, E3SM, Energy Exascale Earth System Model, which is a mouthful, is a fairly sophisticated model that has all of these components, if you can see my cursor here. So there's a land ice component, atmosphere, ocean, rivers, land, human influences, and sea ice. And so what I'm looking at is the sea ice component and then a small piece of the sea ice component. And what we're hoping to do is increase the fidelity of the sea ice model, and hopefully through its coupling to these other components, because these are all coupled together in large scale runs, that we improve predictions overall. Okay, so what's the sea ice component look like in E3SM? It's called MPAS-SI-MPM, where MPAS stands for the type of meshes that are used. That's model for prediction across scales is what MPAS stands for. And these are Voronoi tessellations of the sphere. They can have variable resolution. You can see finer resolution near the coast here and coarser resolution away, for example. And these are unstructured meshes. And the MPAS-SI component in E3SM uses an Eulerian discretization on these polygonal meshes and uses elastic viscous plastic rheology, which is one of the most common rheologies for sea ice. And so that's the starting point for the component in E3SM. Okay, so let me back up a minute here in a sense and just talk about sea ice and why it's important. So sea ice is frozen seawater, and it occurs at high latitudes in the Arctic and Antarctic Ocean and peripheral seas. It's thin, on the order of, say, tens of meters. In fact, if the ice were not moving, if the seawater freezes up in the winter and were stationary, it would get to a thickness about 3 or 4 meters. And because the ice insulates the ocean from the cold atmosphere, you wouldn't freeze any more water. It would just be about 4 meters thick. But on the other hand, its extent is thousands of kilometers. So as you'll see, we modeled it as a two-dimensional system. The other thing is ice. The reason ice is important, sea ice in particular, it's reflective compared to the ocean. You can see in this picture here, the ocean appears darker than the ice. And so the ice reflects quite a bit of incoming solar radiation. And so it's an important aspect of the Earth's energy balance. And there's an albedo feedback mechanism that is thought to enhance climate change. So as the climate warms and you have less ice, then you have more dark ocean, less reflective surface. And so you're reflecting less of the incoming solar radiation, and so you tend to heat more. And so this is a mechanism that is important for studying climate change. Another aspect of sea ice is that when the ocean water freezes, salt gets ejected, and that generates dense ocean waters near the surface, which sink and affect ocean currents. And so those coupled effects are important also. So sea ice is not stationary. It's set in motion by wind and ocean currents, the wind being the major force on ice. And one thing that you can see in this picture here is that when the ice moves, it can fracture and form leads. Leads are areas of open water, or you can just think of them as cracks. And then on the other hand, when you open up these areas of water, you're exposing the seawater to the cold atmosphere. You tend to get a fairly rapid freezing of new ice. If conditions then shift, that ice gets crushed, and you wind up with these features called ridges, where the new ice that formed in these leads piles up on the surface. And so that's a mechanism that allows more ice per unit area than you would have just under equilibrium conditions. So at equilibrium, you would have ice, 3 or 4 meters thick, but some of these ridges can be 30 meters, say. So this sea ice deformation, the motion, the fracturing, the ridging, is actually apparent in satellite images. So these are colored images from processed images from synthetic aperture radar. And what's done is that the retrievals from the satellite are put down in an image. A mesh is laid over top of it, and then the nodes in this mesh are followed in subsequent passes of the satellite. And so you can look at how the nodes move and then calculate deformation. And you can then look at things like vorticity and shear and divergence. And one thing you notice is that you get these localized deformation patterns. They've been called linear kinematic features, they've been associated with leads. So you see that the deformation in the sea ice is not uniform and homogeneous. It tends to be localized. And leads have been estimated to occupy about 2% of the total surface area, but on the other hand, account for about 66% of the heat flux, again, because you expose ocean water to the atmosphere. And I already mentioned that the ridging can result in more ice per unit area than equilibrium thickness. So those are some aspects of sea ice that we're interested in capturing in our modeling. So now let's look a little bit about sea ice modeling in general. So the usual or typical mesh size can be, say, 10 to 30 kilometers. And so you don't have a uniform ice thickness over that length scale. And so that's accounted for with a thickness distribution. So you can think of that as the probability of having ice of a particular thickness within a computational cell. And that thickness distribution is where the ridging and the radiation and the thermodynamics, all of that is in what's called the column physics. And so for each category in the thickness distribution, you have ice of a certain thickness. You then look at thermodynamics and see whether there's freezing to increase the thickness or melting to decrease the thickness, whether there's ridging, which redistributes the thickness. That's all done on an individual column. There's no horizontal coupling. And it also includes things like melt ponds, as I said, the radiation scheme, and also in more sophisticated models, biogeochemistry. And so that's done separately on each column or category of ice in thickness distribution. The horizontal flow, on the other hand, the mechanics, as I mentioned, is treated as two-dimensional and is governed by the momentum equation with various forcing, wind, ocean, Coriolis forces, the sea surface tilt, and then internal forces, which are the constitutive model, how we're modeling the ice itself as a material. Excuse me. So MPAS-SI-MPM, the existing core in E3SM, again, uses these polygonal meshes, MPAS meshes, Voronoi tessellations. The momentum equation is solved at vertices of that mesh, and the column physics is solved at cell centers. So there's a column for each cell, and each cell has a thickness distribution. So that's the existing setup. So with MPM, what the material point method does is add to this Eulerian description of the material a Lagrangian description, a bunch of material points, which are represented here by these blue disks. So the material points carry all the state variables and dynamics variables for the solution of the problem. And what we do is take information that's carried by the material points and project it onto a mesh, in this case, the polygonal mesh, solve the momentum equation on the mesh, and then use the mesh solution to update the material points. And that's in outline what MPM does, and I'll talk some more about it in following slides. This is just an overview. So this gives us a dual description of the ice, if you like, the Lagrangian description based on material points, and then when we project information to the grid, we have an Eulerian description. Why add a Lagrangian description? Well, it's useful for constitutive models when you have history dependence or the fracturing, and it's also convenient for advection. It's a natural way to model advection, because as material points move, they carry all of their information about the state of the ice with them. Whereas if you have a mesh-based scheme for advection, excuse me, you have to solve nonlinear equations on the mesh, and they tend to be diffusive. On the other hand, the Eulerian description is useful for calculating gradients, because if we just had the material points, we need to search for nearest neighbors and somehow compute differences based on material point quantities, whereas mesh-based finite differences are standard and easy to compute. So by projecting information from the points to the mesh and then taking gradients on the mesh, we don't have to do any nearest neighbor searches or direct interaction between material points. It's all mediated through the mesh. And when we transfer information between the material points and the mesh, we interpolate only changes in quantities, and that keeps dissipation small, because you can imagine interpolating back and forth is a dissipative process. So for MPM implementation, as far as the column physics goes, well, IcePack is a standard library for doing column physics. And in the MPAS-Seaice code, that library is called for each cell in the mesh. And with MPM, we just change that so that each material point has its own column physics, and call the same library and have all the same physics available. Now that sounds easy, and in principle it's easy, but getting all of that in the code and being able to switch between using cells and material points, because we want to be able to run the legacy code as well, was quite a bit of work. So that's the column physics part. Again, in theory, easy. And here's a test case of our implementation, just to give you an idea. We call this a Polinia test case. What we do is start out with a cold patch in both air and sea surface. And so that's this square area, and then a warmer surrounding area. And we're not solving the full model, we just have wind blowing from left to right. And so in this area, we will be freezing seawater, so we'll be creating material points, or in the cell, you increase the concentration of ice. And then the wind will blow that ice that's created off to the right, where eventually it'll melt. So here we're testing the freezing and melting and the column physics implementation with MPM. And so what I'm showing on the right is I'm taking a slice through the middle of this domain and then plotting it as a function of time. So time is on the vertical axis, and each one of these is a slice in time. And so here I'm plotting ice volume with the legacy code, and here's ice volume with MPM. And so eventually what happens is you get this steady state profile where you have ice volume building up over this cold patch, and some of it being blown off here past the edge of the cold region and melting. So this is the final profile that we see in both cases. So a little bit more detail about MPM. I want to go through these operations in more detail. So pictorially, what we do in the first step is we have material points, so we take information from those points. You can think of the points as carrying information about a function, whether it's ice concentration or the velocity. And we want to take the information from that scattered set of data points and reconstruct the values on this scattered set of points at mesh points. So in the first step, we're going to map, say, velocity to the mesh, stress to the mesh, snow and ice concentration. So in other words, whatever variables we have on the material points that we need for the momentum solver, we put them on the mesh where we need them. Then in the second step, the mesh has the information that it needs for its solver, so can ignore the material points in this step. And so we imagine computing this solution in a Lagrangian frame so that the nodes of the mesh are moving in the flow. And we can compute gradients of the mesh values in this updated frame to get strain rates. And from the strain rates, we can put that into a constitutive model and get stress. And so, the solution from the mesh is used to update the material points in this step. And then in the last step, we actually move the material points in that computed flow. And so we're interpolating values, really this box and this box, or interpolating values from the mesh back to the material points and moving them. And then we can start over again. We have scattered set of data points, and we can project that onto the mesh and continue. So that's how MPM works. And so I want to show you how this works on the sphere and what we have to do. So when we're working on the sphere, first of all, we're constrained to use the polygonal MPAS meshes because the ocean mesh and the Seaice mesh are the same in E3SM. And so we don't have choice of that. Okay, so now we're working on polygons. The picture that I showed you was for square or quadrilateral meshes, which is where MPM has mostly been implemented in the past. So what sort of shape functions do we use for the interpolation and function reconstruction in these political meshes? That's one first question that came up. The other thing is that we're working on the sphere, so we're working in spherical coordinates, and in particular, lat-long coordinates. And these are actually rotated lat-long coordinates, so the pole of our coordinate system is on the equator rather than at the north and south pole, so that we minimize the effect of metric terms in the actual polar regions on the Earth. And then there's the non-Euclidean geometry that we have to deal with. There's additional metric terms that come up in standard operators. And something that we hadn't thought about much before we started this project, but the parallel transport of vector and tensor quantities. And I'll describe that in more detail. So for the basis functions, there's two types of basis functions that we've implemented and use. One is based on moving least squares. And so we tend to use that in the setting that I've written up here, where P stands for a material point. So we're taking material point quantities, and this is the function reconstruction. We want to get values at other positions from the material point quantities. So what does a moving least square shape function look like? Well, these are quite common in mesh-free methods, if you've seen them. Basically, they're polynomials. So this is just a polynomial in a position x with coefficients that vary spatially. So if you want to determine a function at a position x, you get a set of coefficients for that point. But the polynomial is then multiplied by a weight function, which has compact support in order to take this polynomial that's defined globally and give it compact support to make it more similar to the kinds of shape functions that we're used to, for example, in finite elements. And so these coefficients are determined. You can, moving least squares, you can write it as minimizing an energy function, but equivalently, you can pick the coefficients so that you reproduce polynomials of a given order exactly. And this is just a picture of what one of those shape functions would look like. The footprint, the size of the footprint, and the smoothness are controlled by this weight function. So if you ask to reproduce polynomials, then what you get is this formula for the moving least square shape function. So P is a vector of polynomials. This is the omega is the weight function. And M inverse here is an inverse of the moment matrix, and this is the moment matrix. And so if, for example, we want to get a value at a vertex, and we want to have linear exactness, which means we reproduce just linear polynomials, then we would have in our basis 1, x, y, and z. And so for each point that we wanted to reconstruct the function, we'd have a 4x4 for the 4 coefficients system of equations to solve to determine this shape function. The other shape functions that we use are called Vox-Press shape functions. And we tend to use these in the other direction, taking vertex values and, say, interpolating to material points. And these Vox-Press basis functions actually were used in MPAS-SI in some operations already. They weren't implemented the way that we needed them, so we've re-implemented them. They're generalized barycentric coordinates is one way of looking at it. It's sort of generalize the barycentric coordinates on a triangle to polygons. And one way of computing them is using various areas. So the notation A, X, Y, Z is the area of the triangle formed by these 3 points. And so there are these coefficients C sub I, which are areas formed by 3 consecutive vertices of the triangle. So these vertices, so that would be this triangle here. And then AJ is a function of X, where you look at the point where you want to evaluate the basis function and 2 vertices. So here's 2 of those triangles. And so the basis function itself is a rational function. And it's, you can see it's normalized by the sum of the basis functions at the points. So the basis functions sum to 1. And each one of these components here is this product of these triangle areas. All right, so for these Vox-Press basis functions, they have nice properties if we look at them for polygons in the plane. So they form a partition of unity. As I said, they sum to 1. And they are between 0 and 1. They interpolate vertex data. So if I look at the value at a vertex, I get 1 for the ith basis function at the ith vertex, but it's 0 at the other vertices. And these bases are also in the plane linearly complete, meaning that if I use the shape function against the vertices, then I get the point value in the interior. And they're smooth. There's C infinity in the domain, and piecewise linear on the edges. Now, when you do these Fox-Press basis functions on a polygon on the sphere, it turns out that you can't have both property 1 and property 3 holding. The easiest way to see that is if the polygon had 3 sides, so it was just a triangle. So I take 3 points on the sphere. Well, these properties hold in a plane. So those 3 points on the sphere form a plane. And so if I have 1 holding and then I look at 3, the interpolated value of x is going to be in the plane formed by the triangle, not on the sphere surface. And it is possible to alter the formulas I showed on the last page so that you can require 3 and not 1, but we choose to enforce 1. So I've written the formulas in this way. So on the sphere, we won't have this, this property. Okay, so let's look at the function reconstruction. So in this case, we're going from material points to the grid. And so we're going to use the moving least squares basis functions that I described. So in this example, what we do is assign the material points, give them velocity components. And so the longitudinal component and latitude component, we prescribe different spherical harmonics. And they're shown over here on the right, that on the top, the U and V components. And so those are assigned to the material points. So now we can take those values from the material points and reconstruct values on the grid, and then compare the exact solution, since we know what the spherical harmonics evaluated at the grid point should be, and we can look at the error. And so the middle plot here shows the error at the material point positions. And the bottom 2 plots are also plots of the error, but what I've done is zoomed in on this mesh. And at the center, happens to be a pentagonal cell. If you try to cover the sphere with hexagons, you can't do it with all hexagons. So there's a pentagon in there. And what we were just checking is that there's uniform error when the cell geometry changes. And here we see the L2 norm of the error in the solution. And because we have exactness for linear polynomials, we can see we get 2nd order accuracy in our function reconstruction. So that's the first step of the MPM algorithm, is to take information from the material points and put it on the grid. Now, in the other direction, we want to take information from the grid and interpolate to material points. So, for example, in standard material point method, we would do an operation like this for the position. We take the position, new position would be old position, plus delta t times the vertex velocity interpolated to the material point position. And similarly, the velocity would be updated by taking the acceleration to the material point position. If we do that on the sphere, then points are going, because of truncation errors, we're going to wind up with points going off the surface of the sphere. So what we do instead on the sphere is we update the latitude and the longitude of the material point. And then once we have updated the latitude and the longitude, then we can compute the new material point position. So this is just looking at convergence of interpolation using the Fox-Press basis functions. And what we're seeing here on the bottom, that's for interpolating a constant 1, and you can see that we're at machine precision. So that's the partition of unity property. And for everything else, x, y, z, a quadratic function, a nonlinear function of latitude, the convergence is, we get second order convergence, both for linear and nonlinear functions. So typically in a plane, x, y, and z, or in 3 space, x, y, and z would be exact, like 1 is, but not on the sphere, as I mentioned. So I also mentioned that one of the reasons that it's convenient to have this Lagrangian description is that when material points move, they carry their information with them. And so this is a simple example looking at advection. So here we put down a set of material points to represent ice in this slotted cylinder. Of course, you see that in the Arctic all the time. Just assign a constant ice area, which is actually the concentration of ice. So this is just unit concentration of ice. Here we have a disk of ice and with a distribution of concentration in this cosine bell shape. Here, we're just going to move the material points in a prescribed velocity field. So we're not solving momentum equation yet. We just have a velocity field on the mesh, and we interpolate that to the material points and move them. And this is the velocity field. It's chosen so that these points should move without distortion. And so the velocity has to change from position to position in order to do that. For example, if you're just rotating around the equator, points on the equator have further distance to move than points off the equator. So you have to adjust the velocity in order to keep the shape constant. And so here we're moving at a 30-degree angle to the mesh, and you can see the transport is essentially exact. And just to contrast that with doing a meshed-based advection scheme, if I look at a cosine bell distribution of ice at time 0, use the MPAS advection scheme, which is called incremental remapping. After 120 steps going around the sphere, coming back, this is what that concentration looks like. With MPM, it's basically, in fact, the error is 0 between these. As long as we get the trajectories of the points accurate, then we get the same projection on the grid at the final time as in the previous time. Now this is on a coarse grid, so it makes the mesh-based algorithm look the worst. But even on a coarse grid, we get good advection with the Lagrangian description. Here's a slightly more challenging test problem, testing some of the ridging algorithm. So this is in a plane, not on the sphere. We start off with a square region and just have, so uniform concentration and uniform ice volume to begin with. We apply wind blowing from left to right. And so the ice piles up against this boundary. The concentration is still going to be 1, but the volume, there's going to be a gradient in the volume. And again, in these plots on the right, what I'm doing is just taking the center line solution as a function of x and plotting those in time, where time is going to the right and position is vertical. So, so you can see here for concentration, what we'd expect as you start the wind blowing, the surface this surface is moving to the right. That's what you're seeing here. And then eventually you reach equilibrium, because the ice strength depends on the volume and concentration. And so eventually it doesn't compress anymore, essentially saturate. So that's ice concentration. And for ice volume, you can see that as you're piling it up against the boundary, you have a higher volume against the boundary and this gradient out to zero here. This is ice thickness in the lower left. Thickness is the ratio of volume to concentration, yes, area. What you notice here, maybe you notice, it's subtle in this, but the thickness should be zero. So this blue should actually come out diagonally here. You can see it, see this in the velocity plot, where there's this artifact here. These are the original, this is the original MPAS code. And this artifact is from the advection on the grid. That as you're moving the ice, you're leaving behind a little bit on the grid. And because the concentration and volume are evolving proportionally in this simple one-dimensional problem, the ratio is staying constant. So you have, in this region, you have thickness coming out 0.5, even though both of these are decreasing and getting small. And then you have this artificial velocity in this region. And with the Lagrangian MPM, the material points, once they move out, they don't leave anything behind, and we don't have those artifacts. So again, advection is treated nicely with the Lagrangian description. Okay, so now let's get to a more serious problem. We want to solve the momentum equation. We use the existing solver. We want to leverage that grid solution. So there's no change in the computation of external forces. We are advecting the velocity with the material points. And so the only two terms that we need to consider in the momentum equation are the internal forces and the inertia term. So with MPM, we compute strain by taking gradients of or strain rate by taking gradients of the velocity from the mesh and evaluating at material points. That goes into a constitutive model. Then so we get the stress, then we compute divergence of the stress. And so those are material point operations now. So the inertia term is a little bit interesting. So mass times acceleration. In an Eulerian frame, you would have to advect the velocity field. In a Lagrangian frame, you just have a time derivative here following a material point without these nonlinear terms. That's in flat space. But in on the sphere, if the velocities in lat long components, the base vectors change with time also. And so they have to be differentiated. They vary spatially and as a function and along the material point trajectory. And so there are these metric terms, if you like, that come into the inertia term, even in a Lagrangian frame. And so this is parallel transport of the velocity. Basically, what's happening is that on the sphere, the velocity is in the tangent plane, and then as a point moves, you're moving from one tangent plane to the other. The base vectors are changing, and so you have to adjust the components for that. So just a striking picture to us, because we didn't think necessarily that this was an important term to transport these vector components. But if you start out a point and you give it a velocity and you move it on the sphere, it should move along a geodesic. And so if we have those metric terms in, we do get motion along the geodesic. And because of those metric terms, the latitude and longitude of the velocity vector is, the components are changing as you move, as it should, as you're going from one tangent plane to the other. And if you don't do that, this is what the trajectory of the point would be. As I said, turned out to be quite a striking difference that we weren't expecting it to be that much. Okay, as I mentioned, for the internal forces, we compute a strain rate for the material point, then stress, and then stress divergence. So the strain rate is the symmetric gradient, so just symmetrizing the velocity gradient. And we do this computation in the tangent plane, and we use a mnemonic projection to do it. So this next slide shows that. So mnemonic projection to a tangent plane. So here's a tangent plane at O. Here's a point P on the sphere. The mnemonic projection is the projection from the center of the sphere along a ray intersecting that plane. Now, a nice property of the mnemonic projection is that geodesics map to straight lines in the tangent plane. And our polygonal meshes, the spherical meshes, the edges of the mesh are geodesics. And so we wind up projecting our mesh into a nice set of polygons in the plane. And we use the Vox-Express basis functions on these polygons now in R2 to compute these derivatives. So we would take gradients of the velocity in this representation to get strain rates. And these are just showing the formulas for the mnemonic projection, but the details are not important. And so here's an example, again, taking velocity at material points as spherical harmonics, reconstructing at the material point velocity on the mesh. So we include the function reconstruction. We then have velocity on the mesh. We take the gradients, the way that I just described, to compute strain rate. And so here's the mesh components of the three components of strain rate. This is, again, zoom in near a pentagonal cell. These are the MPM values of strain rate, just the scatter plot of the material points. And down below are errors, again, uniform errors, and showing convergence here with mesh refinement. Okay, the constitutive models are, we've actually implemented 3 of them. I'm just going to mention the last 2 because the simulation I'll show you is with the classical EVP model. So elastic viscous plastic model, let me ignore this time derivative for a minute. The stress is proportional to strain rate. If you look at this, it just looks like a fluid model. And that from here over is actually the viscous plastic model. And the idea behind EVP is to add this fake time derivative. I say fake, it's called elastic, but there's just a single constant here. It's used to just iterate iterate this to a steady state. So it's sort of a regularization parameter, this time derivative. But anyway, that's the EVP model. It's essentially a fluid model with variable viscosity, depending on thickness and concentration for the ice. There's a brittle Bingham-Maxwell model that's been used quite a bit in Europe, which has a true elastic contribution with a viscosity. And I won't go into any more detail on that. And then we've been looking at an elastic decohesive model, which we've implemented, where we treat ice as an elastic solid, but with fracturing. That's what the decohesive part is. And we've only run test cases and not long-scale simulations. So I won't show you stuff from that, but that's where we're headed. And I just want to remind you that just like the velocity components have to be transported, stress components have to be parallel transported also when you move the material points. Stress divergence, we can use stress divergence operators that exist on the mesh. That's our first option. There's actually two that are in MPAS. One is called a variational formulation. It's implemented so that the strain rate is defined at vertices of a cell, and then there's stress computed at each vertex, but that's independent for each cell. So stress is actually multiple valued, where there's a value of stress at this vertex from each of the surrounding cells. So if we want to use that operator, what we do is take stresses from material points on each cell and get a vertex value. Then there's sort of a finite volume, or what's called a weak formulation in the code, where the strain rate is calculated at cell centers, then the stress is evaluated at cell centers, and then stress divergence is calculated doing line integrals around dual cells at these vertices. And so in that case, we would take material point stresses and get a cell-centered value and then go through the MPAS solution. We've also implemented a sort of MPM version of it, where we reconstruct the stresses and then just take divergence applied to that reconstructed stress value. Remember that there's basis vectors associated with the stresses, so those have to be differentiated, and that leads to the standard metric terms in stress divergence. Okay, a quick analysis of the force calculation divergence. So again, assign velocity, get strain rates, reconstruct on the mesh, I should say, get strain rates, get stresses. And in this case, for stresses, we just assign the strain rate to the stress, so no constitutive model. And then take the divergence of that field, which we can compute analytically. So here's the analytical divergence of stress. And these are the various implementations. The first two are actually the original MPAS variational weak formulation. The next two rows are the MPM variational and weak formulations. And the last one is our MPM-based stress divergence operator. And here you can see that there is some bias around that change in cell geometry in all of these. In terms of convergence, the MPM variational form has the worst error. The MPM weak and the original MPAS algorithms basically have the same errors, and our new MPM stress divergence has the least error, but they all have the same convergence rate. All right, so really the last slide here is to look at a global simulation. This is what we call our standard physics configuration. It's so this is a 5-year simulation. This is just an Arctic only mesh, 30-kilometer resolution. We have atmospheric forcing, that's 6-hourly forcing for temperature, specific humidity, wind velocity, and then monthly climatology for cloudiness and precipitation. And ocean forces are taken from previous global climate simulations. And so what I'm showing here is the original MPAS code on the left, the mesh-based solution. So this is just ice concentration over this is the 5-year run. So in the middle, I'm showing the ice concentration from MPM projected onto the mesh. So it should be comparable to the mesh solution in MPAS. Again, we're using the EVP model, so same constitutive model throughout. And then on the right is just the material point representation of the ice concentration. All right. So to wrap up here, what we have is the first implementation of MPM on a sphere, and actually the first implementation of MPM on polygonal meshes that I'm aware of. And I've shown performance of the algorithm on idealized tests and a comparison study on global simulation. And just to briefly mention other aspects of the project, we are implementing the MPM formulation on GPUs. So that's actually going to be the first GPU acceleration that's available for MPAS-Seaice. Because we have this Lagrangian material point method, we can actually add icebergs into our model, and we've done that. So we've added new iceberg physics. We're working on lead detection algorithms for doing error quantification with our elastic decohesive model. So that's taking satellite images and processing to try to identify locations of leads for comparison. Working on metrics to assess model discrepancy. That's particularly important when we get to modeling leads, which are discontinuities. And so metrics like L2 norms don't make much sense. And then we're also looking at emulators for Seaice to use for model calibration and simplified models of Seaice. And so with that, I will stop and almost made it in time, Christian.
Yeah, no, perfect. Great, thank you so much. That was really interesting and really fun to see the simulations too. It's I always love it. Yes, so we can all find the clapping emojis, which are down there. Send those.
Okay, thank you.
If anybody has any questions, if Deborah's got time, then
I do. I'm all yours.
Cool. You can open it up, or I maybe have a couple questions. Thinking about data assimilation for this, and in particular ensemble data assimilation. So it seems like it would be, the material point method, it really lends itself to that, in the sense that you're always going back to this grid where you could do an ensemble update and everything would be aligned because you could interpolate each member back to the same mesh. But I also saw and really appreciated that line of zero concentration, right? So you didn't have this bleed over. One tricky thing with an ENKF is you often get kind of a Gaussian update. So you might actually bleed that edge out into the mean and then affect the members. I wonder if that happened, would that adversely impact the next MPM run? Like, would you want to be very, very careful about creating ice where there was no ice, or maybe the interpolation would handle it okay and just update the points? And
yeah, I mean, it's not something that I've actually worked with. So I mean, a couple of thoughts come to mind. There are algorithms on the mesh that you could do to sharpen the edge. And since the assimilated data in some sense, is not kind of real solution, maybe sharpening it would be okay. And then the other thing is that with the NPM, I mean, you'd have to be careful. I don't know what impact this would have, but if you have values on the mesh, but there's no material points there, then you're in a sense not going to use those values. So now that's maybe a good thing or a bad thing. I mean, it would maybe keep that bleeding from happening on one hand, but on the other hand, maybe you're not accurately taking into account the assimilated data. So it would be a tricky thing to think about, and I don't have a perfect answer. I mean, one could also think about putting material points, where you've spread the edge and just say, okay, that's my new solution. So, so all of those are options. Which one is best and more correct or more useful? That would be open to question.
Right, yeah. It's always the tricky part is figuring those things out. Yeah. Yeah, and it also makes me wonder about doing something like that directly on the material points before going to a common grid and being able to compare those numbers in some interesting way.
Yeah. I mean, there may be a way of sort of using the grid as a scratch pad, but then taking that information back to the material points and then progress the solution from there. That probably would be a good way to think about it.
Sure, yeah. Okay. Anybody else? Before I ask any more, anybody else have any questions? Okay, one thing that was interesting, is the interpolation too, from the I guess the MPAS mesh vertices to the material points, because this is really relevant for JEDI in that when we want to run our observation operators, we map the model for each model that's connected to JEDI to something called a geoval. And I think for MPAS, the way that it works is on the dual mesh with the triangles, and then it's like a barycentric interpolation, basically to say, for whatever observation this is, it's not on a model point, so we need to, interpolate to that spot. So anyway, I guess really this is more of a comment. I'm really interested in maybe thinking about using something a little more clever, especially for that, because MPAS is so unique in this sense. Do you, do you think that is something that it could apply to doing an interpolation this way?
I do. And one thing that came up in this, which I didn't really emphasize in that particular direction, I talked about the transport of the velocity vectors, for example, but I don't know what you do in JEDI, but what they do in MPAS when they interpolate, components and then reconstruct vectors. And what we found to be more accurate actually is the transport vector components to a common tangent plane and then work in the tangent plane. And then with these, say, Voxpress basis in the plane, everything is nice there. And I mean, we have these polygonal grids, but you could project other grids. Again, the nice feature for the MPAS grids is that the edges are geodesics, so then they project to straight lines, and then you have nice polygons in the tangent plane. Other meshes are, the edges aren't geodesics, and so then maybe some other projection is useful. But that's an interesting thing that actually is kind of, we've been tinkering with the code recently, and so this idea of the parallel transport is has played a big role in our implementation.
Right. Okay. Oh, thanks, Ashley. Ashley says, thank you very much, but she has to hop off. So, okay,
Okay.
cool. Okay. Yeah, that's interesting, and it makes me wonder too, working in the plane for things like estimating derivatives for tangent linear models, and yeah, there's a lot of maybe really interesting correlations between the way that you're doing some of these things and what you might want to do for various things in data simulations. So it's super interesting.
Well, I mean, we're preparing a manuscript on this, so hopefully we'll have something that makes sense soon, and be happy to share it with you.
Perfect. Yeah, I'd love to see it.
Okay.
Okay. Okay. Well, let's see. All right. Well, thank you very much. And it seems like, let's see, I guess I'll click stop here. And